Ever wonder if a machine could learn just by watching? Not by being fed the rules line by line, but just by looking at a screen and figuring it out? Well, back in 2013, a team from DeepMind published this incredible paper that did exactly that, using some of the most iconic video games of all time. All right, let's get into it.
It all started with the absolute classics. You remember Pong, right? Just 3 paddles and a ball. So simple, so elegant, and it basically kicked off the entire video game industry.
Or how about Breakout? That feeling of methodically chipping away at a wall of bricks and the pure satisfaction of hitting that very last one.
And then you've got the legend itself, Space Invaders, a true test of nerves, with those aliens marching down the screen faster and faster.
And you've got games like Sequest and Beam Rider 2. Now, each one of these games needs a totally different strategy, a whole different set of skills. So just imagine trying to build one single AI player that could sit down and master all of them.
And that was the whole question. The researchers gave the AI, well, basically nothing. No special instructions, no hints about what a paddle or an alien was. It got the raw pixels from the screen, the score, and a list of possible controller inputs. That's it. It had to learn just like you or I would.
And the results? They were just stunning. The model they came up with outperformed every other approach out there on 6 of the 7 games they tested. This wasn't just a small step forward, it was a giant leap.
So how in the world did they pull it off? How does a program go from knowing literally nothing to playing at a superhuman level? That's exactly what we're going to break down.
So, before they could do anything, the team had to smash through this huge wall in the world of artificial intelligence. It's known as the reinforcement learning problem, and for years, it basically stopped deep learning from working in these kinds of fast-moving, unpredictable situations.
You see, most deep learning back then was what we call supervised learning. It's pretty neat and tidy. You feed the machine a giant, perfectly labeled dataset. This is a cat, this is not a cat. But reinforcement learning? Oh, it's messy. The AI has to learn from rewards that are few and far between. You might not get any feedback that moving your paddle up was a good move until thousands of frames later, when you finally hit the ball and score a point.
The paper actually lays out 3 huge challenges. First, you've got those delayed rewards we just talked about. Second, the data is super correlated. Think about it. One frame of a video game looks almost identical to the next one, and neural networks really hate that. They need variety to learn properly. And third, the data is always changing. As the AI gets better and starts exploring new strategies, the kind of information it's seeing is constantly in flux.
So how do you solve all of that at once? Well, they came up with this incredibly elegant and powerful idea that was the key to unlocking the whole thing. It's called experience replay.
The idea itself is just brilliant. Okay, imagine an athlete. Instead of just rewatching their last play over and over again, what if they made thousands of flashcards of individual moments, good plays, bad plays, everything, from all their past games? Then they shuffle that whole deck and study from it completely at random. That's experience replay for an AI.
So here's the play-by-play. First, the AI just plays the game. And for every single move it makes, it stores that experience, what the screen looked like, what it did, and the reward it got, into this giant memory bank. Then, and this is the key, instead of learning from what just happened, it pulls a random handful of these past memories and learns from that mixed-up batch.
And here's the magic. As the paper says, by shuffling these experiences and training on random samples, it completely breaks that correlation between one frame and the next. This one clever trick solved one of the biggest roadblocks and made the whole learning process stable. It was a total game changer.
Okay, so with the learning problem solved, the team needed an engine to actually do the playing. They needed a digital brain that could see the screen and decide what to do next.
So they built what they called a Deep Q network, or DQN for short. At its core, it's a type of deep learning model called a convolutional neural network, which is just fantastic at understanding images. You can think of it as the AI's eyes and its brain, all rolled into one. The network would take in a small stack of 4 recent game frames, just little 84 by 84 pixel images, to get a sense of motion. It would then push these images through a few layers that are designed to recognize patterns, like paddles or aliens. And the final output? It wasn't just move left. It was a score, called a Q value, for every possible action it could take. It was literally predicting which move would lead to the biggest future payout.
So you've got a clever learning technique, a powerful network, but did it actually work?
This is the fun part. This is the payoff. Let's look at the scores.
This table tells the whole story. Just look at that column on the far right, the DQN. On game after game, it just absolutely crushes the previous AI methods. But the truly wild part is when you compare it to the human column. In games like Breakout and Pong, it doesn't just beat the expert human player, it leaves them in the dust, achieving a level of precision that a person just can't match.
High scores are one thing, for sure, but the most mind-blowing part of this research is how they figured out a way to peek inside the AI's brain and actually visualize its thought process as it played. Okay, so this graph here shows the AI's predicted Q value. You can just think of it as its confidence that it's about to score some points. This is over a quick 30-frame sequence in the game Sequest. Now, let's watch what happens at points A, B, and C.
This is just brilliant. At point A, an enemy submarine pops up on screen. And look, the AI's confidence immediately starts to climb. It knows there's a chance to score. Then, as it fires a torpedo, its confidence just skyrockets, peaking at the exact moment at point B when it expects to make the hit.
And finally, at point C, right after the enemy is destroyed and the points are in the bag, its confidence drops right back to its normal level. This isn't just a program running code. It's a dynamic system that's actively making predictions based on what it's seeing. It's learning.
You see, in the end, this research was never really about Atari games. It was a massive proof of concept. It showed the world that it was possible to build a single, general algorithm that could learn really complex skills straight from raw, messy, sensory data. It was a fundamental step towards general artificial intelligence, and it left the entire world asking one huge question. If a machine can learn to beat us at our own games, what couldn't it learn to do next?